For these theorems, we need to use the definition of a subspace to prove that both the image space, which essentially is the range of the function, and the kernel, which is a set of solutions of the homogeneous system, are both subspaces. So the first part of the theorem is about the image space, and it says that if we have a function that goes from Rn to Rm, the image space, which again is basically the range, it's all the possible outputs of the function, is going to form a subspace. And in addition to that, it's also going to we can also say that a spanning set of the image space is given by the columns of the representation matrix, which are also the same as f of e1, f of e2, etc., where e1, e2, and so on are the fundamental or elementary vectors. So first we're going to prove this for the image space, and then we'll do a similar kind of thing for the kernel. So first of all, what we want to prove for the first part is that the image space is a subspace. So we need to prove that for every y1 and y2 that are in the image space, and for every alpha 1 and alpha 2 that are real numbers, any linear combination of the y1 and y2 is also going to be in an image space. So alpha 1 y1 plus alpha 2 y2 is going to belong to IMF, the image space of the function. So to do that, we're going to start off saying that every y vector in an image space has a corresponding x vector, so it has a solution. So we can say that there exists an x vector 1, in Rn, such that y vector 1 equals f of x1. So basically we plug in the x vector to get the y vector. And same kind of thing for y2. It has a corresponding x vector that we call x2. So since we know that the function is linear, we know that it satisfies the homogeneity and additivity properties, which also means that we can essentially take out any constants, any alphas, and also separate sums. So if we want to take f of alpha x1, alpha 1 x1, plus alpha 2 x2, we can separate the sum, and then we can take out the coefficients, the alphas. So we can rewrite this as alpha 1 fx1 plus alpha 2 fx2. And since we know that f of x1 is going to give us the y1 vector, we can then rewrite this as alpha 1 y1 plus alpha 2 y2. So same kind of thing for the other one. So every linear combination of y1 and y2 is going to be in the image space. And that's going to satisfy the definition of a subspace, which means that the image space is a subspace. So for the second part of the proof, we have to prove that a spanning set of the image space is given by the columns of the representation matrix. So to prove that something is a spanning set, we need to prove that everything in the image space can be written as a linear combination of those vectors. So for that, we say that if we take a y vector in the image space, there's going to be a corresponding x vector that gives you the y vector when you plug it in. And if we take the fundamental vectors, we can say that any x vector can be written as a linear combination of the fundamental vectors. So for example, if you take any random vector like 5, 7, we could rewrite it as 5 times e1 plus 7 times e2, because e1 is 1, 0, and e2 is 0, 1. And if you actually do the multiplication out, 5 times 1, 0 would be 5, 0, and 7 times e2 would be 0, 7. So we get 5, 0 plus 0, 7. And if you add it together, you end up with 5, 7. So the point is just that any vector at all can be written as a linear combination of the fundamental vectors. We also had this in the representation theorem. So we can say that the x vector is equal to the first number x1 multiplied by the first fundamental vector, second number x2 multiplied by second fundamental vector, and so on. So since we know that the function is linear, we can say that our y vector, which is equivalent to saying f of x, is going to be f of all of this that we just wrote out. So f of x1, e1, and so on. And since the function is linear, we have to satisfy the homogeneity and additivity properties. This is something that we also did in the representation theorem proof. And by using the additivity property first, we can separate the sum, rewrite it as f of x1 e1, f of x2 e2, and so on. And then using the homogeneity property, we can take out the constants, so the numbers x1, x2, etc., and rewrite it as x1, f of e1, and so on. So by writing it in this form, we're saying that our y vector here is a linear combination of fe1, fe2, etc., where the coefficients of the linear combination, so what we usually call alpha, they are x1, x2, and so on. So essentially this is your new alpha 1, and this is your alpha n. So since y is a linear combination, that must imply that those vectors, so f of e1, f of e2, and so on, they're going to be a spanning set of the image space. So now for the other proof, we have to prove that a kernel is also going to form a subspace. So this one is actually quicker. It's only going to have one part for the proof. So first of all, the kernel represents the set of solutions for the homogeneous system. So we can say that if we take two vectors that we call x1 and x2 that are in the kernel, they're both solutions of the same homogeneous system. And so f of x1 and also f of x2, they both have to give us the null vector or the zero vector when we plug them into the function, because that's what the homogeneous system is, when you have the function equal to the null vector. So again, if we're trying to prove that this is a subspace, we have to show that we have every linear combination possible in the kernel. So again, using the properties of linear functions, we can say that if we want to take f of alpha x1 plus alpha x2, we can rewrite this, again using the additivity and homogeneity properties, as alpha 1 fx1 plus alpha 2 fx2. And since we know that both fx1 and fx2 are both going to give us the null vector, this will give us alpha 1 times the null vector plus alpha 2 times the null vector again, which will give us the null vector for both. And so still when you add them together, you're going to get the kernel. Or not the kernel, but you're going to get the null vector. So this confirms that alpha 1x1 plus alpha 2x2 is also going to be a solution of the homogeneous system, which means that it's also part of the kernel. And so since every linear combination of x1 and x2 is also in the kernel, then the kernel satisfies the definition of a subspace.